Hello everyone, today we'll be talking about the quicksort algorithm. What is the quicksort algorithm? Basically, it is an algorithm that is using the divide and conquer method to sort the array, similar to merge sort, but here we use pivots. So basically what a pivot is an element in the array, and we shift the element of the pivot. So if it's greater, we shift to the right, and if it's less, we shift to the left. And we keep doing this recursively. And so here we can quickly show you here. This is we'll have something like our pivot right here, and if the element is the val is less than or equal to pivot, we partition it here. Partition, and if it's greater than the pivot, if val is greater than pivot, we partition it on the right side. Partition 2 and partition 1. That's what we're basically doing. Let's make the V clear. Alright, so I'm going to quickly just write the source code, and then we're going to walk through it step by step. Alright? Take a screenshot of this, because I'm going to erase it. If you need it for a note, I'll give it. Alright. 1, 2, 3, 4, 5. Alright, that's enough time to take a screenshot. You can always come back. Alright, let's write our pseudocode. We'll write the pseudocode and I'll explain it step by step, and then we'll go through the recursive walkthrough. Okay. So the first thing we're going to do is, I mentioned, is partitioning. So we're going to have to create our partition function. In a partition function, we will accept the array, the low and the high values. So this is below probably will be the beginning of the array, and the high will be the end of the array. Pivot will be array low, and we're going to have our start and end pointers. Okay, so this will be low, will be high, and we'll keep looping until end is greater than start. Until start is greater than end. And this is how we're going to move our pointers. This is similar to the partition code we had, the partition drawing we had earlier. And we move the start forward here, as you can see. Well, move the we move the end pointer, so the start moves to the right and the end pointer moves to the left. And if the end pointer passes the start pointer, then we stop the loop. And then what we do is, after the start while loop and the end while loop ends, we then do a swap. If the start is still less than the end pointer, with swap. All right. And then while the while loop is finished, we swap the end result array end with first element in the array, which will be low here, and then we return end. Okay. And let's put these stars as comments. This is the code. Okay, this is good for the code. Oh.
Powering off.
This is the partition code here. And let's make it green. Sure. Now we're going to write quicksort. Just call it quicksort here. Array low high. Okay. This is basically our base case because we're going to call recursive statements. Loc, we get our local variable, and so we call the partition function here. Partition array low high then quicksort array loc takeaway 1, you minus 1, you do half of the partition, you do loc takeaway 1, so you do left of the partition, and then here you do the right of the partition. Loc plus 1 until the high, right. All right, this is our function. You can see right here. All right, so now let's go into the code walkthrough. So quickly come here. We're going to choose, so our pivot here will be 7. All right. I'll show you here. And let's make our main function here, whatever. The main, let's just write a main function. Let me just quickly write this main function down. The main function here. And we'll just say, call this quicksort. Array 0, take away the size. Okay, it's our main function. Okay, this is our function here. This is okay. So let's quickly draw this out. So we are right here. So we go, okay, 0 and 7. 0 is less than 7. That's the high. And we are right here in the partitioning stage. Let's make this red. We are here in the partitioning stage of the function. So, have recall. So, what you do here is, in the partitioning stage, we have our start variables, start and end pointers. So what we're going to do is just going to make start and end. We're going to switch it to S and E to keep it short. Okay. So S here, change the color. 7, 6, 10, 5, 2, 1, 15, and E. All right. So we're going to quickly go through this coding walkthrough. And the pivot is 7 here. So is 7 less than or equal to 6? Yes, that is true. Is 7 less than or equal to 10? No, it's not. So we stop this while loop right over here. We stop, okay? We move S here. We move S to 10. Sorry, change color. S to 10. Now we're going to execute in this function right here at the end. All right. So what we do here is we go, is 15 greater than 7? Yes. 1 greater than 7? No. We stop E here. And then we do a swap. Swap 1 with 10. And this is now oopsie doopsie. That should be white. 1 is all right. Now we continue. We go back up here. So you can see, all right, is 7 less than is 1? Yes. Is 7 less than 5 or equal to 5? Yes. Is 7 less than 9? No. We stop over there at 9. So let's put our marker S here. And now we execute the while end loop. And we go, okay, is 10 greater than 7? Yes. Is 2 greater than 7? Nope. So we stop it there. And then over here, what we do now is we swap 2 and 9. Awesome possum. And then we continue. Is 7 greater than, is 9 greater than 7? Sorry. Is 2 less than 7? Yes. Is 9 less than 7? Nope. So we stop here. Okay. And then we go, is 9 greater than 7? Yes. Is 2 greater than 7? Nope. So we reach the end of this loop. Reach the end of this loop. Start now officially. Start is not less than end. So we exit the loop and we do the swap. We'll swap right now. We're going to swap end with the first element in the array. So 2 and 7 are now going to get swapped. Let me just draw that out for you here. Here. Two and 7. And now this here, the function here is the partition code. Partition in the main function. Now, if we draw here, I can show you. We are now here. We're going to partition the left side of the array. Pivot is 2 here. Oh. Sorry about that. So we go our local. So here our local variable here is returned 7, right? But we're going to partition, as you can see, loc takeaway 1. So loc takeaway 1 here, we're going to partition right over here, loc takeaway 1. And then loc plus 1 is going to be partitioned here recursively. We're going to partition recursively until low is greater than high. So as you can see, we're going to go to loc takeaway 1 now. So we're going to go here. and partition 2, 6, 1, and 5. And the pivot here is 2. Pivot is 2. Okay. I also have to draw in the source code where we are right now. In the main function, this is it within the main. This is not, the red mark does not count for the recursive call. So as you can see, we're here. We're just going to quickly go through the stuff. Okay. S and E, the pivot is 2. All right, so you, is 2 equal or less than 2? Yes. Is 2 less than or equal to 6? No. So we stop it here, move S over here. Now we do E. Is E greater than 2? Yes. Is 1 greater than 2? No. So right here we just do a quick swap. One and 6. And then you can say, then we go back to the start loop and we go, all right, is 1 less than 2? Yes. So is 6 less than 2? No. So you can see right over here that we put start. Okay. And now we're at the end loop. So you can sit 6 greater than 2, yes. 1 greater than 2, no. So we end it here. And we exit the loop since start is greater than end. And we do our final swap. Oopsie doopsie. This is the result. And we go here. We go back recursively. This is lock plus 1 here. And this is loc takeaway 1. So let's go here. One, 6, and 5. You can see right here. 1 is already solved, as you can see. So we're going to go here, and we know the answer to this one. So we do a swap here. We're going to go fast. Five and 6. All right. Lock. This is lock takeaway 1. The recursive calls. So as you can see right here through this the function quicksort array lock to equal 1 on this function, we did make a recursive call on lock plus 1 we did recursively call this one anything here on the right. The partition to the right was this quicksort array lock plus 1 and high was called on the right side, and lock takeaway 1 was called on the left side. Just note that, take note of that. This is how the recursion tree works for this function. All right, now we're going to do this one. All right. Nine, 10, 15. This is lock plus 1. Okay, we know the answer for this one. We don't have time to break it down. So here it is lock plus 1. And here the pivot would be, pivot is 9. 9's the pivot. So you go here recursively, this here, it's already sorted, so this is lock plus 1, this is lock takeaway 1, and you can see here that 9, 10, and 15. If you really want to get technical, break it down even further. Let's say to this, breaking down to this. And if you same applies for 5 and 6, so if you break it down technically, 6, and you can see this is 5. So now if you go here, we're going to sort the array. I'll just follow these steps. Let's choose another color. Let's choose green. The array sorts itself. So you follow. Here you go. 5, 6. You traverse through here. You go 7, 9, and you go 10 and 15. So the sorted array, the result is 1, 2, 5, 6, 7, 10, and 15. Result. Okay, we sorted the array. So I forgot to tell you, when we go to 7 here, in the main function, not recursively, quicksort is being called, as you can see. So quicksort loc plus 1. So I could see. So if you see lock takeaway 1, So if you see lock takeaway 1 here, that means it's linked to quicksort lock takeaway 1, this function here. If you see lock plus 1, it's linked to this function being called here. And then it keeps going down until you can't break it down anymore. Until the start is greater than the end. That's the base case. So look, remember that when you see anything on the right side of the tree is lock plus 1, anything left side of the tree that's broken down to partition is lock takeaway 1. So I repeat, partition to the left is lock takeaway 1, partition to the right is lock plus 1. All right. So I'm going to say in the main function, I want to repeat myself here. Let's change this here to here is quicksort. It is this function here from 1 to 7 right here. This function is being called in the main function, or in the main code, not, and this one here in the main 9 to 15, it's being called on this line, but recursively will call on the left side lock takeaway 1. Recursively will call this function on this side nine, 10 on this side here on the left side. We'll recursively call this function on the left side here. And break it down. And it would also recursively call quicksort plus 1 on this side. You guys get it. I know it's a lot of a mess, but I did my best at trying to explain the recursive tree here. All right. Actually, now let me get the eraser. I'm just going to do a quick drawing for you guys, and then I'm going to explain the time complexity of this function, and then we'll be done. Okay, let's quickly show you here. Pivot. Just want to quickly show you. I want to probably repeat myself here again, but whatever. Here, it's partitioned in half. Recursively, this is quicksort array. This here is high. Sorry. Look plus 1. High. So I got this one mixed up. sorry. This one, the first recursive call. And this one's, let's make this one yellow. And just keep drawing this one out. Okay. So here, undo that one. For this side, see if I could copy. See what? Oh, I didn't change the color. Here. Copy. I can't. I have a hard time copying, pasting. Copy. And on this side here, take a screenshot of this. This is how the recursive calls are happening in the quicksort function. I broke it down recursively. Look at the function. It connects to the code. So I'm just going to connect this code here. So as you can see, right here, I'm going to connect it to the function. As you can see, quicksort local. And this one's here is linked to here. All right, guys, take a screenshot of this. This is how the recursive calls work in quicksort. And let's break down the time complexity on this. The time complexity best case is n of log n time. Worst case is quadratic time. Worst case n of 2 time. All right, thank you for watching. I hope you enjoyed this video and see you guys soon.